Welcome to this presentation on the BoSL low-cost velocity sensor. So in this experiment, we are going to gather data from BoSL and HAC velocity probes, evaluate the effectiveness of the BoSL velocity probe, and identify improvements which can be made to its design. First, an introduction. Water velocity is the bulk speed at which water is moving. However, there are a few caveats to this. So, not all layers of water may be moving at the same speed, and so ideally we want to measure the average speed of all water in the flow. Principle of measurement. So we're going to use what's known as the Doppler effect, and this is where sound waves which are reflected off a moving object change pitch. You may have experienced this if you're listening to an emergency siren drive past. It'll increase in pitch first and then decrease as it drives off. So in water, we have suspended particles of bubbles, impurities, and other things which move along with the flow, and this is what we use to bounce our ultrasonic signal off. More specifically, we have an emitter and a receiver, and the emitter emits a 1 MHz ultrasonic sound, and it bounces off the suspended particles in the water. Then we listen to the shifting frequency of the reflection. So we have another ultrasonic transducer or receiver, and this converts the ultrasonic sound into a voltage we can measure. We note that when the reflection occurs, we go from a high frequency to a lower frequency, which we can see in the diagram as the spacing of the wavelets. So with this signal from the receiver, we need to first amplify and clean it before we can use it. There aren't too many particles, particularly in clear water, and so the reflected signal is very weak. And so we have some circuitry on the velocity sensor which cleans it up and amplifies it to a usable state. Once we do this, we pass the signal through an FFT, and this is an algorithm which generates a velocity spectrum plot, which essentially is a plot of the strengths of the components of each velocity. So at the left of the plot, we have the strength of low velocity components. At the right of the plot, the strength of high velocity components. And the way we determine the velocity is we look at this spectrum and we see where the highest measured velocity is, the amplitude of the highest velocity. And here is the BoSL velocity sensor. You can see the two transducers in the front, and it integrates this Doppler shift measurement principle. It's also low power and low cost. And you can see it's also quite small in size. So for our site setup, we installed the sensors at Dandenong Creek. We have the HAC and BoSL probes installed so we can compare their measurements. And the HAC probe also uses the Doppler shift technology to measure the water velocity. The BoSL velocity sensor, its data is logged with an Arduino and it's uploaded live to the cloud every 2 minutes. There are plans to migrate to the BoSL data logger, however, this is pending on some changes to sort of what voltage is required for the sensor, which is in the works just after we get verification that the sensor is working. The HAC data, that needs to retrieve manually every week, and it logs every minute. So we plot the measurements that we received from the 20th of the 6th to the 25th of the 6th. Our BoSL measurements are in orange and the HAC data is in blue. The y-axis, we have velocity measured in millimeters per second. We can see that the profiles of the curves are similar. They increase at the same points, decrease in the same points. However, there are a few key differences. So the first is there's a much wider variance from point to point in the BoSL sensor. It will measure anywhere between what looks like the maximum of what the HAC will measure to 0. And it will do so randomly from point to point. The second key difference is that there are these sporadic readings, which read at about 3.5 millimeters per second. They're not very dense, they may be 1 every 100 points, but they are present. So we can come up with a hypothesis as to what's causing some of these issues. We hypothesize that the random variance is caused by slower moving particles in the water, so perhaps heavier particles don't move at the speed of the water, but move at a fair bit slower. And so if these reflect the signal stronger, they may lead to that having the highest amplitude, and thus that being what we record the velocity as, despite the fastest particles in the water moving at a faster speed, close to the true speed of the water. Similarly, it might be the fact that the interaction of different water layers moving at different speeds might cause certain layers to reflect the ultrasound signal more, and thus, if they're moving slower, they'll also cause this same effect. And so an idea is, perhaps instead of measuring the maximum velocity, we should measure the falling edge of the velocity profile. This is because we don't expect any particles to be moving faster than the water velocity, and so the falling edge, when it goes from a high signal to a low signal, should give us an indication of the speed of the fastest particles in the water, which is close to the true speed of the water. So the hack also logs the depth, and we can use this for two things. First of all, we can get an indication of rainfall events, and we expect that when the water level increases, that indicates a rainfall event, and we do see in our data that the velocity increases when the level increases, and which is what we expect. We expect there to be more flow when there's rain, and that is what we're measuring. Secondly, we also see that the sporadic readings occur at low water levels. And the reason of this may be that there isn't enough water depth for the velocity probe to have particles to bounce the ultrasonic signal, and so the signal may be weak. Now, this may cause random noise effects, which are very small when the water level is high, to become much more prominent, and they might randomly cause the peak of the FFT of the velocity spectrum to be at the 3.5 meter per second mark. So we may need to investigate the detection of low signal levels to distinguish between when the sensor sporadically reads at this level and when the water velocity actually is traveling that fast. Another thing we can do is plot the Hacke velocity versus the BoSL velocity. And so we expect, if we use the Hacke velocity as an indication for the true velocity of the water, all the points to be on a one-to-one correlation line, which would indicate that our sensor measures the true velocity of the water. We see that this is not the case, that our sensor often reads below the one-to-one correlation line. However, we do note that it tracks well to it, in the sense that the top of the correlation set of points does follow that one-to-one line fairly well. And we see that the sensor reading below, this supports our hypothesis of the measurement of slower moving particles in the water. Because if it's measuring slower moving particles, we expect it to measure below what the fastest velocity is, or the velocity of the water, which is what the Hacke velocity measures. Secondly, we can see where the sporadic measurements appear in our correlation plot, and when we do that, we see that they appear far up the top of our plot, well separated from all the rest of the points. And this tells us that it is a separate effect which is causing this sporadic measurement to be occurring, and that it's not, it's likely not to be due to the quality of the readings that we're getting. So from this we can draw a few conclusions. Our first conclusion is the measurement principle is demonstrated viable in a low-cost design. We've shown that the Doppler shift can be implemented cheaply and measure fairly well the trends, velocity trends, similar to Hacke in its current state. However, work needs to be done to improve the repeatability of the readings, and particularly getting rid of that wide variance in the data. We also note that the low velocity levels cause instability, and so that leads us on to our future works. The first one is we want to find a better method of inferring the bulk velocity from the spectrum. So we've discussed the highest amplitude method and the falling edge idea. We want to test both of these to see which is better, or perhaps if there's another way which more accurately tells us the speed of the water. We also want to verify that the variance in the measurement is caused by slower moving particles. And another thing which might be interesting to test is detect if the velocities at different layers of the water are discernible from each other. And this perhaps opens up the possibility of measuring the velocity at different depths, which would provide more data on the exact flow profile of the site. And finally, we want to make the sensor BoSL compatible, so it can be used without data loggers, which can go about a year without needing to have their batteries replaced or maintenance. On the progress of these, so for the first two, we have a new in-field test site set up, and this is recording not only the velocity but also the entire spectrum. And so we'll take this data back and we'll run some detailed analysis on it to see what's the best method for determining the actual velocity from the spectrum. And hopefully from that we'll be able to develop an algorithm which we can implement on the velocity sensor so that it will automatically be able to tell us the reading of the water velocity. For detecting the difference in velocities between different layers, calculations indicate that we'll need more precise time measurements and more data to be processed. To do this, we'll need to upgrade the processor of our sensor, possibly in a further iteration or a new version of the sensor. And some work on this has already been done, looking at different processors that we're able to use. Finally, for BoSL compatibility, solutions and ideas for how to do this are in progress, and some are being manufactured, waiting to be tested and evaluated. Thank you. This was an update on the BoSL velocity sensor.